Next, NASA recently announced that its Voyager 1 probe, the most distant human-made object in the universe, is once again sending usable information to Earth. This follows months of receiving garbled data. While humanity has explored the solar system to a remarkable depth, new discoveries continue to astonish us. For years, we believed we had identified all the planets, only to be proven wrong. What about the Voyager probes? How far have they ventured beyond our solar system? Even scientists are amazed by the groundbreaking revelations from these spacecraft. One of the most fascinating discoveries is that our entire solar system, including the distant Oort Cloud, which lies about a light-year from the Sun, is encapsulated within a colossal bubble. This bubble spans 1,000 light-years across, with the Sun remarkably positioned near its center. But what exactly happened as the Voyager spacecraft crossed the edge of the solar system? Could we truly be trapped in a massive space bubble? And how does this discovery reshape our understanding of the solar system's dynamics? Let's dive in to find out. On September 5, 1977, NASA's Voyager 1 spacecraft launched from Cape Canaveral, Florida aboard a Titan Centaur rocket, just weeks after Voyager 2's launch on August 20. Originally designed for a 5-year mission to study the outer planets, these resilient probes have surpassed all expectations, continuing to send data back to Earth more than 44 years later as they venture into interstellar space. The Voyager missions capitalized on a rare planetary alignment that occurs once every 176 years, allowing the spacecraft to perform gravitational slingshots from one planet to another, conserving their limited fuel. Despite launching second, Voyager 1 was the first to reach Jupiter and Saturn, focusing on these planets, while Voyager 2 explored Jupiter, Saturn, Uranus, and Neptune over a decade. The data transmitted by the Voyagers have profoundly shaped our understanding of the outer solar system, earning their place in textbooks and media alike. As a unique touch, each spacecraft carries a golden record, a time capsule of Earth sounds and music intended to communicate with potential extraterrestrial life. As of January 2024, Voyager 1 is approximately 14.9 billion miles, 158 times Earth's distance from the Sun, from our planet, making it the farthest human-made object in space. Voyager 2 achieved a major milestone in November 2018, becoming only the second spacecraft to enter interstellar space, following Voyager 1's breakthrough in August 2012. Voyager 1's departure from the heliosphere, the vast bubble of charged particles created by the Sun, was confirmed when its plasma wave instrument detected a massive solar eruption between April 9 and May 22, 2013. The eruption caused nearby electrons to vibrate, and researchers found that the surrounding electron density was significantly higher than that within the heliosphere. This data revealed a surprising contrast. Interstellar space is denser than regions near the Sun, but the heliosphere's outer edge is much less dense than areas closer to Earth. By analyzing this data, scientists pinpointed Voyager 1's official entry into interstellar space to August 25, 2012, using electron oscillation measurements and observations of charged solar particles. Voyager 2 followed suit, crossing into interstellar space 6 years later, confirming the profound scientific significance of the twin spacecraft. The data from the Voyager spacecraft reveal many similarities, such as the overall density of particles encountered in interstellar space. However, their journeys revealed notable differences, sparking new questions about the Sun's trajectory through the galaxy. Outer space continues to defy our expectations, and Voyager 2's observations as it crossed the heliopause, the boundary between the heliosphere and interstellar space, are shedding light on some of the solar system's greatest mysteries. To understand Voyager 2's groundbreaking findings, it's essential to first grasp the Sun's dynamic nature. Far from being a tranquil ball of light, the Sun is a star, a blazing nuclear furnace hurtling through the galaxy at approximately 450,000 kilometers per hour. Its surface is a tangled web of magnetic fields, driving a continuous flow of electrically charged particles known as the solar wind. This solar wind streams outward in all directions, carrying the Sun's magnetic field across vast distances. Eventually the solar wind meets the interstellar medium, a region filled with remnants of ancient stellar explosions. Much like oil and water, the solar wind and the interstellar medium don't easily mix, creating a boundary called the heliosphere. This vast bubble, powered by the solar wind, extends roughly 11 billion miles from the Sun, encapsulating the Sun, all 8 planets, and a significant portion of the solar system's outer regions. Strange, isn't it? But it's the kind of strangeness that works in our favor. The heliosphere acts as a protective shield, guarding everything inside, including us, from the galaxy's most dangerous radiation. Without it, life as we know it would be exposed to potentially catastrophic hazards. The outer edge of the heliosphere, called the heliopause, marks the beginning of interstellar space. Understanding this boundary has profound implications for comprehending the Sun's movement through the galaxy, as well as the conditions around other stars scattered across the cosmos. Scientists are especially intrigued by the interactions at this threshold, how the solar wind and interstellar medium mix, the extent of material exchange across the boundary, and the dynamics of this cosmic collision. When Voyager 1 crossed the heliopause in 2012, it provided the first-ever glimpse of this mysterious region. However, interpreting its data posed challenges. Scientists discovered that the interstellar magnetic field was 2 to 3 times stronger than expected, suggesting that interstellar particles exert up to 10 times more pressure on the heliosphere than previously thought. Still, Voyager 1's revelations were incomplete. Its plasma instrument had failed in 1980, leaving gaps in the data. Voyager 2, however, provided a breakthrough in 2018. With its plasma instrument fully functional, scientists gained a clearer view of the heliopause. They observed that as the spacecraft approached the boundary, the surrounding plasma slowed, heated up, and became denser, offering an unprecedented look at the dynamics of this crucial interface. The interstellar medium beyond the heliopause is far hotter than expected, with temperatures reaching at least 54,000 degrees Fahrenheit. However, because this plasma is incredibly thin and diffuse, the average temperature around the Voyager probes remains extremely low. Voyager 2 also confirmed that the heliopause is a porous boundary, allowing particles to pass in both directions. For example, Voyager 1 encountered 10 streams of interstellar particles that penetrated the heliosphere, resembling tree roots breaking through rock before fully crossing the boundary. Meanwhile, while Voyager 2 detected a subtle flow of low-energy particles extending more than 100 million kilometers beyond the heliopause. As Voyager 1 approached the boundary, the outgoing solar wind slowed dramatically, creating an eerie limbo-like state. In contrast, Voyager 2 observed a unique transitional layer in the solar wind, similar in width to the stationary zone observed by Voyager 1. This disparity underscores the complexity of the heliosphere and highlights the need for more data to unravel its mysteries. The solar system appears to be as adaptable as a chameleon, with puzzles that demand a broader understanding of the heliosphere. Voyager 1 exited the heliosphere leading edge where it collided with the interstellar medium, while Voyager 2 left through its left flank. However, we still lack information about the heliosphere wake, leaving its overall shape uncertain. The heliosphere could be spherical due to interstellar medium pressure, but it's also possible it has a comet-like tail or a glass-like shape. Unfortunately, current spacecraft won't provide answers. NASA's New Horizon spacecraft, though fast, will run out of power in the 2030s, over 1 billion miles short of the heliopause. This limitation has sparked calls for a follow-up interstellar mission, a multi-generational effort to explore the farthest reaches of the solar system and beyond. With data from only 2 points, we cannot fully grasp the heliosphere structure. More data is essential. Voyager 1 also made another fascinating discovery beyond the heliopause, a persistent hum. Upon entering interstellar space, the spacecraft's plasma wave instrument detected oscillations in the interstellar gas caused by solar activity. However, between these eruptions, the instrument also captured a faint continuous signal. This low-frequency hum, though monotonous and feeble, suggests that the interstellar medium contains more subtle activity than previously understood. By monitoring this hum, scientists can better map the spatial distribution of plasma in interstellar space. These findings allow researchers to study the interplay between the interstellar medium and the Sun, with the solar wind, the stream of charged particles perpetually flowing from our star, playing a crucial role. Together, the Voyager missions have provided invaluable insights, but they also highlight how much remains to be explored in the vast frontier beyond our solar system. In the past, measuring interstellar plasma relied on chance events triggered by solar activity, but that is no longer the case. Thanks to Voyager 1 and 2, we now have an incredible trove of data about interstellar space gathered over decades of exploration. These spacecraft have continually exceeded expectations, astonishing scientists with their capabilities. Their discoveries have unveiled the immense power of cosmic radiation and shown how charged particles from the Sun and other stars interact. New insights into Uranus, decades-old Voyager 2 data reanalyzed. For nearly 40 years, scientists have based their understanding of Uranus on data collected by NASA's Voyager 2 spacecraft during its historic flyby in 1986. Recent reanalysis of the data has revealed that our conclusions about Uranus's magnetosphere and its moons were likely incomplete due to a rare and coincidental solar wind event during the spacecraft's brief encounter with the planet. When Voyager 2 flew by Uranus, it captured groundbreaking data, including the discovery of new moons and rings. However, its observations of the planet's magnetosphere, a protective magnetic bubble shielding Uranus from solar wind, were puzzling. The magnetosphere appeared unusually empty of plasma, leading scientists to believe Uranus had a magnetosphere fundamentally different from other planets in the solar system. Recent research shows that this anomaly was caused by a solar wind event that compressed Uranus's magnetosphere and pushed out plasma. Such events are extremely rare, occurring only about 4% of the time. If Voyager 2 had arrived a few days earlier or later, it might have observed completely different conditions. The updated analysis sheds light on several key mysteries. Scientists previously believed the lack of plasma indicated that the moons were geologically inactive. The new understanding suggests that this conclusion was premature. Uranus's 5 largest moons could in fact be geologically active, possibly harboring subsurface oceans or other dynamic features. The solar wind event likely energized Uranus's radiation belts, contributing to the unusually high levels of charged particles observed by Voyager 2. These findings may help explain why Uranus's radiation belts are second only to Jupiter's in intensity. This revised understanding of Uranus emphasizes how critical timing and conditions are during planetary flybys. The findings also highlight the importance of long-term observation missions. Scientists are advocating for a dedicated mission to Uranus to explore its atmosphere, magnetosphere, and moons over an extended period. Such a mission has been prioritized in NASA's Planetary Science and Astrobiology Decadal Survey. Voyager 1's revival of a 43-year-old transmitter. In a stunning display of engineering foresight, NASA's Voyager 1 spacecraft recently communicated using a backup radio transmitter that had been dormant since 1981. This milestone highlights the ingenuity and resilience of the spacecraft, which is now over 15 billion miles from Earth, making it humankind's most distant emissary. In October 2024, Voyager 1 experienced a communication anomaly when it unexpectedly ceased sending data via its primary X-band transmitter, which operates at higher power and provides more detailed telemetry. Engineers detected a faint signal from the spacecraft using the backup S-band transmitter, which consumes less power but has a weaker signal strength. This transmitter had not been in use for 43 years, and its activation likely resulted from the spacecraft's automated fault protection system, designed to conserve energy and ensure operational longevity. Detecting Voyager 1's S-band signal posed a significant challenge given the spacecraft's immense distance and the faintness of its transmission. Using its highly sensitive array of antennas, NASA's Deep Space Network managed to capture the signal, verifying the spacecraft's operational status and enabling the team to maintain communication. However, the S-band system, designed as a backup, lacks the capability to relay detailed telemetry, limiting the mission team's ability to assess Voyager 1's full health and performance. This incident highlights the exceptional foresight behind Voyager's design, which incorporated redundancies for critical systems to ensure long-term mission viability. NASA engineers are now carefully evaluating the potential to reactivate the X-band transmitter, a crucial tool for transmitting detailed data while minimizing risks to the spacecraft. The event serves as a powerful reminder of the complexities of deep space communication, where even minor malfunctions demand meticulous troubleshooting due to the nearly 2-day round-trip signal delay for command responses. How far will Voyager travel in a billion years? In a billion years, the Voyager probes will have journeyed far beyond the realms of the solar system into the vastness of interstellar space. By that time, Voyager 1 and 2 will be unrecognizable as they continue to drift, their instruments long silent due to their power sources running out. However, they will still travel through the galaxy on a path that will eventually take them 50,000 light-years away from the Sun across the Milky Way. Voyager 1 is currently heading toward a distant star called AC plus 793888, and Voyager 2 is on a trajectory toward Ross 248, a star in the Andromeda constellation. However, these stars will only come close to the probes in tens of thousands of years as the Voyagers continue their journey. The most exciting revelation in the next 3 to 5 years will likely be something we can't even imagine yet. But if you're feeling adventurous, take a guess, you might just be right. If you enjoyed this deep dive into Voyager 2's journey, don't forget to like, subscribe, and click the bell for notifications on our next episode. Thanks for watching, and we'll see you next time.